So I teach a class right before this. So sometimes I notice like I get this ping in my email that someone has joined this class before I'm out of the other class. So if you ever join it and it says that I'm not here or whatever, just like hang on a second, because that means I'm finishing up the other class and I'll be there like pretty quick or whatever. Okay, so let's see. Last time we did a bunch of stuff regarding order of operations, getting a handle on doing like sort of complex fractions and things like that with denominators and denominators and numerators and stuff like that. And then we moved at the very end onto linear equations, which is where we're gonna be for the next like couple of days. So we're gonna start by reviewing that, do several examples, and then I have some for you guys to work on that are related to the examples that we will just do right now. And like I did last time, I'll try to come around to as many of the groups as I can during the time that you guys are working on them to talk through them with you. And then the next thing we want to get into, which we'll start today, is linear inequalities. Okay, so let's go ahead and look at some more examples of linear equations. So last time we had these kind of allowable actions that produced an equivalent equation given kind of a starting point. And you could perform those allowable actions until you have like the variable by itself. Essentially, that's what's going on. So let's maybe start with, let's just jump right into examples. So let's maybe start with this one. So we have 3 minus 1.7t equals t over 4. And let's say, well, we only have one variable there, so we want to solve for that variable t. Notice we have this kind of mixture of things going on. We've got a whole number there. We've got a decimal there, so 1.7. And then we've got a fraction here. We've got like 1/4 t. So we somehow want to put all of these things together so that we can combine them more easily. So even though it's maybe not what's preferred at the moment, we really want to default to putting everything into fractions. And that's not because there's something special about fractions with how you combine them as numbers. It's because a lot of the calculation techniques, what we'll be moving forward with when we're dealing with like more complicated expressions and equations, and the kind of calculations that happen in a calculus class will involve like working with fraction expressions instead of decimal expressions, because there'll be variables and stuff. So that being said, that means we want to take this 1.7 and then write it as a fraction first. So let's maybe do that. So we have 3 minus, so 1.7, so that's going to be like 17 over 10. And then we can just go ahead and put that t in the numerator, equals t over 4. Now, the next thing that I would like to do, now you have two choices here. You can either add 17 over 4t to both sides, or you can look at this thing, and since it's an equation, I can take this whole equation and multiply by something, which will cancel out all of the denominators. And it's like really useful to cancel out all the denominators, because then you will have only an equation without fractions involved. So that means we need to multiply by something that will cancel this denominator here and this denominator here. So 20 will be maybe your best choice in this case. It's like the least common multiple of 10 and 4. Okay, so now let's see. 20 needs to get distributed to all of these terms, and then we'll see what we get. So 20 times 3, so that's going to be equal to 60. And then we have 20 times 17 over 10. So maybe let's write this out in detail. We have 20 times 17 over 10 t equals, and then this is going to be 20 times t over 4. And then let's do the simplification. Now, you can maybe like do this simplification before you do the distribution, but just to be safe for the first time or two, we'll do it like this. So notice we've got 20 over 10. We can cancel that down to a 2. We've got 20 over 4. We can cancel that down to a 5. Now we can go ahead and distribute. Well, not really distribute, but multiply this 2 and the 17. That's going to give us, we still have a 60 here minus 34t equals 5t. Now we can move the 34t over. That gives us 60 equals 39t. In other words, t equals 60 over 39. Now we maybe like to reduce that to lowest terms. Notice that the numerator and the denominator have a factor of 3. So we can divide the numerator by 3 and the denominator by 3. And that leaves us with 20 in the numerator and 13 in the denominator. And so that's maybe the simplest, because now there's no common factor in 20 and 13. You can't simplify it anymore. Okay, cool. So let's maybe do a couple more of these. So let's say something like this, maybe 3x minus 4 over 2 plus 1 equals 2x. So again, you can take the same strategy we had right here, which is multiply by something in order to totally cancel out the fractions, and you're left with a simpler looking equation. Or you can combine all of the fractions together. I'm going to go ahead and maybe we'll multiply by something to get rid of all the fractions. So we want to think to ourselves that all of these can be written as fractions. It's just those have a 1 in the denominator. And now we can take this entire equation and multiply by what happens to be the least common multiple of those denominators. So 2 and 1 and 1. So we're going to multiply the whole thing by 2, because that's going to have the effect of canceling all the denominators. So let's see what we get. So we'll take this 2, distribute it on to all parts of this equation. And a really important thing here is to remember that being inside a big numerator like that is being grouped together and being like in parentheses. So when we distribute it, we have to keep that in mind. All right, great. So now let's see. We distribute this, and we'll have 2 times the quantity 3x minus 4 over 4 plus 2 equals 4x. So that's what we get from moving all of that through. But then we really chose this 2 for the express reason that it would cancel this thing out right here. So that 2 cancels with that 2. And now we're left with 3x minus 4 plus 2 equals 4x. And we can start simplifying. So we can combine the negative 4 plus 2 to get negative 2. So we've got 3x minus 2 equals 4x. Now we can subtract 3x from both sides. And that leaves us with negative 2 equals x. But generally, you want to write this in the order x equals minus 2. So you have something like that. So I think maybe the takeaway from this is, if you have an equation, if you can multiply by something that really gets rid of all the fractions. So that, that would be my pointer or my hint, or maybe a good strategy. So eliminate fractions by multiplying the whole equation by something. And that's something that's going to be different depending on what the equation is. So, but in short, it's the least common multiple of every denominator. So we look at all of the denominators here. We had 1 as a denominator, 10 and 20. So the least common multiple of 1, 10, and 20 is, 1, 10, and 4. So the least common multiple there is 20. And then here, the least common multiple of 2, 1, and 1, well, that's just 2. Okay, great. So let's do another one. I want to do 2 more that just have a single variable, and then a couple that have more than one variable, and you solve for one of them. And these last 2 with a single variable are going to be a bit complicated in that they have like radicals kind of built in. All right, so let's look at this. So 8 times y times the square root of 3 plus 1 equals 7 minus the square root of 12 times 5 minus y. Okay, so since we're trying to find an exact solution, we want our solution to involve the square root of 3. We never want to like punch it into our calculator and say, oh, the square root of 3 is 1 point, whatever, 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 because that's just an approximation. And that approximation, well, I mean, that's fine for some uses. And, you know, it's actually kind of fine for finding a solution to this if our goal was not to like develop the skills that we're trying to do for calculus or whatever. So we want to keep all of the exactness of having square roots of 3 and stuff in here. So just like as a heads up, your solution should look like this. Y equals, so this is going to be a bunch of stuff with square roots of 3. That's just a number. I mean, it's maybe not a number that like you want to deal with a lot, but it is just a number. Okay, so let's see what we can do for that. So maybe the first thing that I would like to do is notice that this square root of 12 can be simplified. And we can do that by thinking of this as the square root of 4 times 3. So 4 times 3 is 12. And we're kind of motivated to do that factoring because that's under a square root, so we want to factor out a perfect square. So we can factor that perfect square of 4 out of 12. Now let's just go ahead and rewrite this real quick using that fact. And then on top of that, we can take this 4, bring it out of the square root by taking the square root, and that'll give us a 2 outside of the square root. Okay, so now we have 8y times the square root of 3. So that's what's happening right here. Plus 1 equals 7 minus 2 times the square root of 3, and then 5 minus y. So that's what we get after simplifying this thing that I did in green. And now we're ready to go on to the next step now that this is simplified. So now I want to take this negative 2 square root of 3, and I'll distribute it onto both of these terms. So let's see, the left-hand side of the equation is going to stay the same. So we'll have 8y square root of 3 plus 1 equals 7. So if we multiply that first one, so this is going to be like that times that. So we'll have minus 10 times the square root of 3. So you have 2 square roots of 3. You multiply it by 5, so you're going to have 10 square roots of 3. And now we're going to have a minus sign times another minus sign. So a minus times a minus is a plus. So that's going to give us plus 2 square roots of 3 times y. Okay, good. Now we're going to want to move all of our numbers to the one side of the equation and all of our things with y to the other side of the equation. Keeping in mind that all of the numbers could have a square root of 3 built in. And all of these things with y could also have a square root of 3 built in. So notice the things that I underlined in blue have a y in them, and then the things that are underlined in this peach color don't. They're just numbers. So let's go ahead and maybe take care of this. We'll subtract 1 from both sides. That's going to give us 8 times the square root of 3 times y. So I just rearranged this a little bit, just to put all the numbers out front so it looks closer to that. You can put this in any order you want, but I really just wanted to make those look more similar to each other. So this is going to be equal to 6 minus 10 root 3 plus 2 root 3y. Now we can go ahead and take this minus 2 root 3y and take it over to that side of the equation. So let's see what that leaves us with. Okay, so we have like terms here. We have 8 square root of 3y minus 2 square root of 3y. So that's going to cancel down to 6 square root of 3y. So we have 6 root 3y. 8 minus 2 is 6. And then the root 3y you can think of as like the term there. And then we're left with this stuff on the right-hand side of the equation. So 6 minus 10 root 3. So 6 minus 10 root 3. Okay, good. Now, we want to get the y by itself. So look at what we've got. It's kind of ugly, but essentially what we have is some number times y equals some other number. It's just the number that we have in front of the y is the 6 times the square root of 3, and the number that we have on the right-hand side of the equation is that like crazy combination. But we do the same thing that we would do if those were more familiar numbers. We just divide by 6 times the square root of 3 on both sides. So we'll divide by 6 root 3 here. We'll divide by 6 root 3 here. That's going to give us just y on the right-hand side of the equation because these guys cancel. Sorry, on the left-hand side of the equation. And then on the right-hand side of the equation, we'll have 6 minus 10 root 3 over 6 root 3. And this is like the answer. That's just a number on the right-hand side of the equation. Maybe it's not like beautiful. It's not like the number 6 or 42 or 73 or whatever, but it is a number. There's one thing that sometimes is commonly done with this, and that's called rationalizing the denominator. So this is going to be something we look at like quite a bit more carefully later, but sometimes people get a little squeamish about there being square roots and stuff in the denominator. So we can get rid of those by taking this whole fraction and multiplying by the square root of 3 over the square root of 3. So that's just like multiplying by a fancy version of 1. You know, anything divided by itself is 1, so that's okay. And then notice that it has this nice effect in the denominator that when you take the square root of 3 and multiply it by itself, you get 3. So that means the denominator is just 18 because we got 6 times 3. And now the numerator, where you're going to have to distribute it through, but you'll get something kind of similarly nice. So you'll get 6 times the square root of 3 minus, now this is going to be 30. Again, and it's 30 because we have 10 times the square root of 3 squared, but that's going to be 10 times 3. And now we can actually simplify this a little bit more. Notice that you can factor a 6 out of the numerator and a 6 out of the denominator. So here you have a 6. 30 is like 6 times 5, and 18 is like 6 times 3. So we can go ahead and write this as 6 times root 3 minus 5 over 6 times 3, just like factoring that like as needed. And then these 6's cancel, and you're left with root 3 minus 5 over 3. Yeah. And so that is, it's the same as this number right here, but sometimes like you want the simplest possible version, and maybe this is the simplest possible version of the solution. Okay. So let's do another one that is kind of like this, involves some square roots and stuff. Yeah. And then we'll look at some that have more than one variable where we solve for a particular variable. Okay, so let's say, here's our next one. Let's say it's 4x plus 1 over 3 equals x times the square root of 18 plus 2. So there are like two things that you would maybe want to do first. The first thing is to like look at your radicals and see if your radicals can be simplified. That is, see if you can like factor some perfect squares out of the numbers in your radicals. That would maybe be one good first choice. Another good first choice would be to multiply by something so that the fractions are gone. Both of those are good first choices. Maybe let's do the radical simplification first. So this is in a square root. So that means we probably want to factor 18 so that it has a perfect square as a factor, but we can do that. That's the same thing as 9 times 2. So 18 is 9 times 2. So this thing is the square root of 9 times 2. But we can pull the square root of 9 out of the radical by taking its square root. When we take it out of the radical, the square root of 9 is 3, so that just becomes 3. So now let's go ahead and rewrite that using that calculation. So we have 4x plus 1 over 3 equals 3x times the square root of 2. And then plus 2. Yeah. So here we just took the 9 out of the square root and it became a 3. Now let's go ahead and multiply by something so we have no fractions, keeping in mind that everything can be viewed as a fraction with a denominator of 1 if necessary. So here we need to multiply by 3 because that's the least common multiple of all of the denominators that we see. It's going to multiply through all of those, keeping in mind that being inside a big numerator like that is like being in parentheses. So notice the 3 times this will just cancel the denominator. So that gives us 4x plus 1. The 3 times this is going to give us 9. I'm going to reorder this a little bit. Times the square root of 2 times x. So I just did 3 times 3 is 9, and then I just switched the order of those to put the number out front and the variable at the end. And then plus 6, because that's 3 times 2. Now we want to move everything with an x to one side of the equation. That's like that, and everything without an x to the other side of the equation. So that's like that and that. So we'll start by maybe subtracting this 9 times root 2x from both sides. So that's going to give us 4x minus 9 times root 2x. And then maybe we'll simultaneously subtract 1 from both sides. So if we subtract 1 from both sides, we get that's equal to 5. Okay. Now this may seem like, well, we can't simplify this, and it's true that we can't simplify this maybe as much as we'd like to, but we have an x in both of these terms, which means we can use the distributive rule in reverse to factor it out. So if we do that, we can factor the x out, and we're left with 4 minus 9 times the square root of 2 equals 5. So notice if I were to distribute this x through, I would regain the last step. So I've just factored it out. But that is good because now, well, I'm just going to copy this back up here. Okay, so just copying this back up here, we have x times 4 minus 9 root 2, and then equals 5. So essentially what we have is the same thing as before. We have some number times x. Notice the numbers to the right, but that's the same, equals some other number. It's just the number is not very nice. It's this 4 minus 9 root 2 thing. So we would probably like to divide by that number that's multiplying x to get rid of it. So we'll divide by 4 minus 9 root 2 divided by 4 minus 9 root 2. So that's going to give us x equals 5 over 4 minus 9 root 2. And there's also a way to simplify this to make it so that the denominator does not have a radical. It's called multiplying by the conjugate. And maybe I'll write that down real quick, but we won't do the calculation because this is something that we'll dive into more later. But if you multiply the numerator and the denominator by this kind of sort of complicated thing, then you'll get a different form of the solution. And sometimes that different form is preferred. Although it's not that big of a deal. We can just stop at this point right here. Notice it's not great, but we do have x equals, this is a number because it's a number divided by a number. So we have a solution. Okay, good. So now what I want to do is do maybe 2 examples or 3 examples or something where we solve for a given variable, then break you guys apart to do some of these. Like I said, I'll come around to the groups like I did last time, you know, as time allows, and then we'll look at inequalities. That's how we'll finish it off. Okay, so let's start with this. Let's say we want to solve for y. Let's say we have 3y plus 2x equals x minus y plus 5. So we've got 2 variables here. We've got x and y, and they're all mixed together in this equation. But our goal is to like get one of them by itself. So it kind of depends on what setting you're in, which one you want to solve for. But at this point, I'm just saying, hey, we're going to solve for y. So that means we want to move everything with y to one side of the equation. So maybe we'll like blueprint out what we're going to do. So everything with a y will move to the left side of the equation, and then everything without a y. And here's the like important difference when we've got these more than one variables. It's not just going to be move all the numbers to the other side of the equation. It's going to be everything without a y. So we'll move that to the other side of the equation. And there's nothing special about this going to the left and this going to the right. They just have to go to opposite sides of the equation. Okay, good. So now let's go ahead and do this yellow box action. So that means we need to add y to both sides. So that'll move everything with a y to the left. So let's see what that gives us. So if we add that here, we get 4y plus 2x equals, so now we're going to have x plus 5. Right? So the y's cancel. That was our goal. And now we move everything without a y to the right. So that means we'll want to subtract 2x from both sides. That's going to leave us with 4y equals negative x plus 5. Then we're almost there. We don't have y by itself. We have y multiplied by 4. So we can divide the whole thing by 4. And that leaves us with y equals minus x plus 5 over 4. And then we have it. So we have y completely by itself. So we've sometimes this is we'd say like we solved for y in terms of x. So we didn't completely solve for y because it depends on this other variable, but we solved it in terms of x. Okay, let's do another one. So let's say maybe this one is also solve for y. So we'll say x times the quantity. 3 minus 2y equals 5y. So there's a little bit more going on here. There's some simplification that needs to be done at the very first step and at the very last step that was not required over here. Like over here, everything was broken apart into different summed terms. But over here, we've got like a distributive rule type thing that we have to take care of first. And then we can start moving everything with a y to the left, everything without a y to the right. But we're not there yet. So let's go ahead and break this down by using the distributive rule to multiply that x through. So that's going to give us 3x minus 2xy equals 5y. So the important thing here is this is 2 times x times y. So we're going to have to, that's going to make it a little trickier at the end, but it shouldn't be too bad. Now, move everything with a y to the left, everything without a y to the right. So this has a y, we'll move that minus 5y, and then minus 3x, minus 3x. So notice these guys are going to cancel over here, and these guys are going to cancel over here. And we're left with minus 2xy minus 5y equals minus 3x. Now, this is like pretty similar to one of the ones that we just did with a bunch of...
Professor?
Yeah.
Could you minus 3x to the right side and then minus 5y to the left? And then just add 2x to negative 3x?
Yeah. That'd be, if I'm following correctly, I think that sounds fine.
Okay, thank you.
So I think you mean move, instead of moving that way, move that way, right? Like kind of swap the sides of the equation? Yeah, that'd be fine. That maybe be easier here for what it's worth. Okay, so now we've got something like this. And then this is actually fairly similar to one of the ones we did with the square root involved. It's just we have an x there instead of a square root. We're still trying to get y by itself. So let's see. We can factor the y out of both terms in the left-hand side. So if we do that, we'll have a y, and then left we'll have minus 2x minus 5 equals minus 3x. And this is actually a good place to be because we've got y times something equals something. This is the only occurrence of y, so we can divide by that big something. So we'll divide by minus 2x minus 5 on both sides, minus 2x minus 5. So let's see what that gives us. That gives us y equals minus 3x over minus 2x minus 5. But I mean, in my opinion, that's like not, we can make that more aesthetic. We've got all those minus signs there, right? But we can cancel all those minus signs if we want to. And technically what we're doing here is taking the numerator and multiplying by -1 and the denominator and multiplying by -1. And this wouldn't have been required if we had done it the way that you suggested. Like we would have skipped this. But that will give us y equals 3x over 2x plus 5. So we get the same kind of thing. Good. Okay, let's do one more, and then we'll do some. Okay, so let's say this one, let's solve for x. And here we have y minus y0 equals m times x minus x0. So here we've got lots of things that are just like letters. We want to solve for one of them, right? So the way that what's going on here is like this is x term is somehow being preferred, and it's different from all the others, and so we want to get that totally by itself. And all the other parts are like either different variables or they're different numbers, but they're just, we don't know what the value is. Okay, so let's see what we can do. We can start by distributing the m to both sides, sorry, to both parts of the right-hand side. That'll give us y minus y naught equals mx minus mx naught. Then what we can do is maybe we'll add mx naught to both sides. And I guess like, just to be really, really careful, notice that x naught and x are not the same, right? That's, they have similar symbols for each of them is using a similar symbol, but they're different things. Okay, so let's see. That is going to cancel this mx naught from the right-hand side and leave us with y minus y naught plus mx naught equals m times x. But now we're in a good spot because we've got m times x equals a bunch of other stuff. So we can just divide both sides by m, and that's going to cancel that out. So here we'll have y minus y naught over m plus x naught. So I did a little trick here where notice this m and this m will cancel, but only there. And then this is equal to x. So there, we solved for x, and then maybe if you wanted to just move the x over to the left-hand side of the equation, we would have x equals that. So we've got x like totally by itself. Again, there are maybe like two good first steps. One is to try to simplify the roots as much as possible. Another one is to maybe try to get rid of the denominators. In this case, maybe I'll get rid of the denominators. So we can take this whole thing and multiply by 3 because we see that like 3 is the least common multiple of all the denominators that we see. We've got a denominator of 1 and a denominator of 3. So let's do that. So that's going to give us 3 times the square root of 50y. We're not simplifying this just yet, but we almost will. And this is going to be equal to 6 minus the square root of 8 times y. And then notice that 3 over 3 canceled, so we've got no longer fractions involved. The next thing that we want to do is try to simplify these square roots as much as possible. And maybe the hint that you should be able to do that is the fact that you've got 2 different numbers under the square roots, and they probably can be simplified in a way so that you have the same number under each square root. So let's go ahead and maybe do these separately. So this square root of 50. So the thing is we want to factor 50 so that it includes a perfect square. So we can factor that like 25 times 2. So that's a factorization of 50 that includes a perfect square. And then we can go ahead and bring this 25 and factor it out of the square root by taking the square root. That'll give us 5 times the square root of 2. So that's what we'll replace this 50 with. Well, sorry, the square root of 50 will be replaced with 5 times the square root of 2 in the next step. Now let's do the same thing for this radical 8. So if we've got the square root of 8, again, we want to factor it so that it includes a perfect square because that'll give us some simplification. So we can do that like the square root of 4 times 2. And then same kind of thing. So notice 4 is a perfect square. That was the whole point for factoring it like that. So we can bring that 4 outside of the radical and it becomes a 2. Square root of 4 is 2. So we've got 2 square root of 2. So that means we're going to take this one up here and rewrite it as 2 times the square root of 2. And that's actually good news because notice that means this like square root of 2 type thing is our like term. So we made these two parts look pretty similar. Okay, so injecting that in here, so we have 3 times 5 is 15 square root of 2 times y, and then equals 6, and then we have minus 2 square root of 2 times y. Now we want to move all the y's to one side of the equation and all the numbers to the other side of the equation. So we can start that off by adding 2 root 2y to both sides, so plus 2 root 2y. So we've got 15 root 2 plus 2 root 2, so that's going to be 17 square root of 2y equals, and then all that's left on the right-hand side is 6. So again, this looks maybe like kind of gnarly, but it still is just a number times y equals a number. And so you'll approach that just as if it were a kinder number. So maybe we can divide by this number, which is in this case 17 times the square root of 2. So we divide this by 17 root 2 on both sides. So 17 times root 2. That's going to leave us with a y by itself on the left-hand side. And then on the right-hand side, we have 6 over 17 root 2. And then I think that's like a fine place to leave it. At this stage, you can like simplify it by doing this thing that we talked about before, rationalizing the denominator, where we multiply by the square root of 2 over the square root of 2. That's going to give us 6 times the square root of 2 on the top. And then this square root of 2 times the square root of 2 on the bottom will multiply together to get 2 times 17 is 34. And then maybe you could reduce that. Notice that we can divide 2 out of the numerator and the denominator. That'll give us 3 times the square root of 2 over 17. I don't know. None of those numbers are better than the other numbers, though. So any of those would be fine. 2x plus 1, and that's in parentheses, equals x times the square root of 7 over 9. Okay, so I would say there are 2 good first steps here. One would be to distribute this minus sign through to both of these. And the other one would be to multiply the whole thing by 9 to get rid of the fractions. Maybe I'll go ahead and just distribute this minus sign onto both of the terms that are inside of the parentheses, just because we have to choose one of them to do first. So let's go ahead and take that minus sign, distribute it on both of those. So that's going to transform our equation to 4 minus 2x minus 1 equals x times the square root of 7 over 9. Now we could go ahead and multiply everything by 9, but at this point, we might as well just do this 4 minus 1, like combine the like terms as we can. So that's going to give us 3 minus 2x on the left-hand side equals x times the square root of 7 over 9 on the right-hand side. Now we can start transforming this so there are no fractions anymore. So again, think of this as like fractions with a denominator of 1. So if we want to cancel those out, we can multiply the whole thing by 9. So let's see. That's going to give us 9 times 3, so 27, minus 9 times 2, so that's 18x. And then this is going to be equal to x times the square root of 7. And that's as simple as you can get it. And I guess I should say you might want to see if you can simplify the square root of 7 by factoring the square root of 7 so that it includes a perfect square. But it's impossible here. I mean, 7 is prime, so it doesn't factor at all, let alone factor where you can take a perfect square out of it. So this is like as simple as you can make it. But that is something like to pay attention to and make sure that you can't simplify this anymore. Okay, great. So now let's go ahead and we can move all the x's to one side and all of the not x's to the other side. So I'll just like add 18x to both sides. So that's going to leave me with 27 by itself on the left. And then on the right, I'll have 18x plus x times the square root of 7. So I'll go ahead and bring that up here, but I'm not going to change anything. I'll just maybe change the equation. So just flip the equation. So we'll have 18x plus square root of 7x. That's another thing that I'll do. I'll just like switch that so the number's in front. Again, it doesn't really matter one way or the other. Equals 27. So I've just rewritten the equation a tiny bit. Now I can factor an x out of the left-hand side. You shouldn't really do that until you get everything with an x on one side of the equation, but we have that. We have everything with x on one side of the equation, which means we can factor the x out. So if we factor the x out, we're left with 18 plus the square root of 7. Now, just to check real quick that we did the right thing, notice if we distribute the x onto both of those, we get right back to the last step, so everything looks okay. And so this is going to be equal to 27. And now, even though this is like kind of gnarly looking and not super nice, it still is x times some number equals some other number, which means you would approach this the same way as if that were a kinder number like 5. You would just divide by 5 in that case. But here we've got to divide by that whole like chunky thing, which is 18 plus root 7. So that's what we'll do. We'll divide both sides of the equation by 18 plus root 7. 18 plus root 7, and that leaves us with x by itself on the left-hand side, and then 27 over 18 plus root 7 on the right-hand side. And like I kind of mentioned earlier, you can, I don't really like using the word simplify here because it's not exactly simplifying. You can simplify this by getting rid of the radical in the denominator, but we're going to look at that a lot more closely later. So this is an appropriate way to leave this for now. So this is essentially the same thing as a linear equation. It's just you have a greater than or equal to or a less than or equal to sign instead of an equal to sign. So let's recall that we had some allowable actions for equations, and here we have the same allowable actions with one difference. So same allowable actions, except one thing, and that is if you divide or multiply by some negative number, you have to change the direction of the inequality. So maybe let's write it like this: change direction of inequality. So here's like an example with numbers to give us some sort of intuition for why we have to do this in the first place. So 3, I think we can all agree, is less than 7. But now let's go ahead and multiply both parts of this inequality by -1. If we multiply both sides of this inequality by 1, we get -3 and -7. But -3 is bigger than -7, right? Yeah. So let's maybe look at another one real quick. So let's say x is bigger than 4. But that means that -x is less than -4. So those are equivalent. So essentially what's going on here, and I like thinking of it like this, it's really you're doing some sort of reflection. So notice if you've got the origin here, so the point 0 here, and then let's say you've got this open interval 4 to infinity in that direction. So multiplying by a minus sign essentially reflects it about this line here, and it reflects it over here. But notice that that reflection puts the arrow pointing in the other direction. So I don't know. I like thinking about things geometrically like this, but as long as you just remember the rule that you have to swap, you know, not to belittle it, but swap which way the alligator's eating, right? Then you're good. Okay, so let's look at an example or two. So let's say our first example looks like this. 2 minus 3x over 4 is bigger than or equal to x plus 3. So the important thing here is that you're not going to get a single number. Like with our linear equations, we got x equals a single number. X equals 5, x equals -7, x equals something gnarly like the square root of 2 plus 1 over something else, right? But it was always equal to a single number. We won't get that for inequalities anymore. So let's see what we get here, but the strategy is still the same. You want to do the same allowable actions like getting rid of fractions and doing all that kind of stuff. Just keeping in mind whenever you move a minus sign across the inequality via multiplication or division, you have to switch the direction. Okay, so kind of motivated by what would happen if we had an equal sign there instead of an inequality there, we want to multiply the whole thing by 4. Because one side has a denominator of 4, one side has a denominator of 1. So multiplying this left-hand side by 4, it'll cancel that and leave us with 2 minus 3x, bigger than or equal to, so we've got 4x and then plus 12. Now, next thing that I'll do is, well, I mean, you've got some choices, right? Do you want to move your x's to the left or your x's to the right? It's kind of the same. I'll move them to the left just so that we have to do this for practice, but you can move them to the right. That's also fine. So if we subtract 4x from both sides, and then maybe we'll also subtract 2 from both sides to move all the x's to one side and all the numbers to the other side. So notice that 4x is going to cancel that 4x, that 2 is going to cancel that 2. And we will be left with minus 7x is bigger than or equal to 10. Something like that. Now we've got to divide by -7. So if we divide by -7, we get x over on this side, and we get -10 over 7 on that side. But then our inequality had to change because of this rule right here. So now it's going to be x is less than or equal to -7 over 10. But now remember, the very first day of class, we did some stuff with interval notation and stuff like that, and then that continued into the second day of class. And there was a reason why we did that, and it wasn't to make the first day of class seem completely different than all of the other days. It was so that we could write down solutions to this using that interval notation. So that's what we'd like to do. Write down this in interval notation. So in interval notation, so that's going to be all values of x that are less than or equal to -10 over 7. So, you know, even when it's not super necessary, I like to work through the graph. So here we would put -10 over 7 on the graph, put a closed circle there because we've got a less than or equals to, and then we shade to the left because it's going to be, like I just said, less than or equal to. Now we can turn that into an interval, -infinity up to -10 over 7. We've got a parentheses on the -infinity because infinity always gets a parentheses, and we have a bracket on the -10 over 7 because we are including it. So, I mean, now there's a little bit more motivation for looking at the interval notation. Okay, so let's do one more. And I should say that these inequalities, you're going to always want to put them in interval notation. We developed that interval notation because it's a good tool for communicating solutions to inequalities like this in a concise way. Okay, so let's look at one more. So this is like a compound inequality. So it goes like 1/2 is less than or equal to 2 minus y over 3, which is less than 5. So I want to point out that this is an and statement, and we'll look at compound inequalities more next time. Ones where you have to really use the fact that it's an and statement carefully. You don't really have to do that here. But what this means is that this thing in the middle is bigger than or equal to 1/2 and less than 5. Okay, so we do the same thing that we did before. It's just now we've got 3 sides of the inequality. We just have to do the same thing to all 3 sides. So we've got some fractions involved. Notice our fractions involve this 1/2, this 3, and this 5. So we could maybe multiply the whole thing. Sorry, this 1 in the denominator there. That's the denominator there. We want to multiply by 6 because that's like the least common multiple. Okay, so 6 times 1/2 is 3. So that's going to be less than or equal to. Now 6 over 3 is 2. So that's going to give us 2 times the quantity 2 minus y. Because the 6 over the 3 cancel each other down to just 2. Right, so maybe just as a heads up, this came from 6 over 3 times 2 minus y. So the 6 over 3 is 2. And then 6 times 5 is 30. So now we've got this, still a compound inequality. We can distribute this stuff on the inside. That'll give us 4 minus 2y. And then the other 2 sides are unchanged. Now we can start subtracting 4. So we'll subtract 4, but we have to do that from all 3 portions of the inequality. That leaves us with a -1 over here, a -2y over here, and then a, 26 over here. Now we do one more thing. We've got to divide by -2. I don't know why this became yellow. So we divide by -2. So that's going to leave us with a 1/2 right here. That's going to leave us with a y right here. And that's going to leave us with a -13 right there. But since we divided by a -2, we've got to switch the order of all of these. So now it goes like this. So now, more carefully, you would maybe write this from least to greatest. So this would be -13 is less than y, which is less than or equal to 1/2. And then in interval notation, that's going to be -13 to 1/2. We do not include -13, but we do include 1/2, so we have parentheses bracket. Okay, and then, I mean, we're essentially like 45 seconds overtime or whatever. So this is like where we're going to do this kind of similar stuff with inequalities instead of just equalities, and motivate why we did interval notation in the first place.